Now we're ready to start chapter 17, and that's all about what happens when waves come together. One major difference between waves and particles is that two objects cannot occupy the same space. So think about if you're playing pool. The two pool balls can't be in the same place at the same time. But two waves can definitely occupy the same space at the same time. An example of that would just be sound. You can listen to two people talk at the same time. So two sound waves can be together at your eardrum at exactly the same time. So what we're going to do in this chapter is develop a way to analyze what happens when two waves exist in the same space at the same time. First, we'll take a quick look at some examples and then develop some technology. The first set of wave interference we'll look at now will be waves on a string because it's really easy to visualize. As a reminder, a wave on a string is just a pulse that goes down along the line. If it hits a barrier, it's going to bounce back. That's something we'll talk about more, but this is just a place where we're going to start. If you wanted to open up a simulation and fool around with this a little bit yourself, if you Google PhET wave on a string, it'll bring you to the string page. And then the conditions you should try would be pulse, a loose end, and no damping. So here's what one wave on a string looks like. Next, we'll look at what happens if we have two waves on a string and what happens when we come together. So in this little bit of a simulation, we have two waves. One approaches from the left, one approaches from the right. They hit the same spot on the string, and then they carry on moving. What's interesting about this, or what things do we need to think about? When the waves come together, we see that they get bigger. Both of the individual waves are both upright. So this is our first case that we're going to look at, and after we're finished looking at a couple of examples, then we'll develop some definitions and stuff. So in this case, we have two waves moving towards each other. Once they're on top of each other, they get bigger. Once they're past each other, they just carry on as though they had never met. Next, we'll look at an example where they're not both upright. In this bit of a simulation, we have two waves. The wave that starts from the right is upside down. The wave that starts from the left is right side up. So now these guys point in opposite directions. When they meet, it's kind of interesting. They still overlap. At one point, it goes exactly to zero, and then they pass on through just like they never met before. So some things are in common with the one we saw on the last slide, and some things are different. So something that's the same is that the two waves meet. They do something when they meet, and then they pass on by. The thing that's different is what happens when they meet. So it looks like that difference happens because of the nature of the waves. In the first example, they were both upright. Here, one's upright and one's upside down. So now we're ready to move on and make some definitions. Our first definition is the principle of superposition. Superposition says that if two or more waves are simultaneously present at a single point in space, so if we have two waves at the same place and the same time, then the displacement of the medium is the sum of the displacements of each individual waves. So it says that if we have two waves come together, the new wave is the sum of those individual waves. In math terms, so here in the top picture, we have one wave moving to the right. We might say that the height of that wave is d1. Remember, d1 is a function of position and time. Then we have a second wave that's moving to the left. So this is like the first simulation we saw, the two upright waves coming together. So our second wave is moving to the left. It has a height that we'll call d2. And again, that's a function of horizontal position and time. When those two waves overlap, it makes a new wave, which is the sum of those two waves. So the height of the superposition, sometimes we call that the resultant, and we put an R around there, is equal to the sum of wave 1 plus wave 2. So that's superposition, and it applies to all different kinds of waves. Of course, we'll look mostly at some special cases, but this is true for all waves in general. When we have superposition of waves, so waves coming together and adding together, that's often referred to as interference. So the two waves meet, they interfere to make a new wave. We have two kinds of interference we're going to talk about. The first goes with the first simulation we looked at. If we have the two upright waves coming together, when they combine, they made a bigger wave. This is called constructive interference. So constructive interference occurs when two waves combine to create a wave that's larger than either of the individual waves. So that's our constructive interference, when they come together to make a bigger wave. The other kind of interference we have is called destructive interference, and that goes with our second simulation. We had an upright wave and an inverted wave. When they met, they made a wave that was smaller, and that's our condition for destructive interference. Two waves combine to create a new wave that's smaller than at least one of the individual waves. With destructive interference, we do have one special case of perfect destructive interference. That happens when the two waves combine and they completely cancel out. And that might just happen for a short time, but we will see perfect destructive interference from time to time. So that's when the two waves completely cancel. But destructive interference in general is just when they make a smaller wave. So we've said we're looking at interference of waves. Now we'll specify that we're talking about traveling waves. So if we have two traveling waves, it's important to identify where the wave's coming from. In our simulations we looked at, one wave comes from the source, then that wave travels down the line until it hits a barrier and it reflects off the barrier. We will talk about the nature of that reflection, but for now it's enough to know that it does reflect off the barrier. So our two waves are the incident wave, that's the one made by the source, and the reflected wave. So there's two waves that we have. Those two waves come together, they have interference, could be constructive or destructive, but we know that there will be interference. And we're going to look at special cases that occur depending on how the source emits the waves. So what if our source is continually making waves? Then the waves continue down the line, they continue to reflect off, so there are always waves being produced and interfering. It turns out we can get a special circumstance of what happens here. So this is one picture. I keep shaking one end of the slinky, the wave travels down, waves bounce back. And if you look at that slinky, sometimes when it's moving, kind of looks like a wave that's staying still. Like you can see the motion going up and down, but the wave picture itself kind of stays a bit constant. Okay, that's one picture. We'll look at one more picture. So these are still waves on the slinky. I'm just shaking one end a bit faster. Hopefully you can see the wave pattern happening here. You can even try and draw on top of it and see what happens. So it looks like it comes up on one side and down on the other side. There's a wave there. And there's the down part right there. Hopefully that's going to come through. That's so hard to draw on a trackpad. So it looks like it makes a standing wave, and this one would have exactly one wavelength. So standing waves is something that we're going to study because there's all sorts of applications, and Justin might even try and get you to do a lab on this one. This is a nice picture of a standing wave on a string. It's set up on an oscillator and taken with time-lapse photography. So on the left we have an oscillator moving with simple harmonic motion. It pushes a string up and down. A wave travels down the line, reflects off a stand on the right end, and that reflected wave travels back. So the wave coming from the right interferes with the wave coming from the left. Because the waves are made by an oscillator moving in simple harmonic motion, both of the waves, the one made by the oscillator and the reflected wave, those are both sinusoidal. They have the same frequency, same wavelength, same amplitude. One of the waves is moving to the right, one is moving to the left, and then the two of them together, when they interfere, they make that standing wave pattern. So we can try and highlight what the picture is showing us. It shows, because it's time lapse, it shows that the string is moving between different extremes. So I'm trying to highlight in green here. This is one extreme of what the string looks like. So at one spot in time, it follows that green line. Pick blue for the next color. Then a little tiny bit of time later, it moves down a bit, and then moves up on the bottom, down on the top. Then a little bit of time later, I'll go red, A little bit of time later, passes straight through the middle. Oh, the red I think was a bad choice. Then a little bit of time later, I'll go with yellow. It's going towards the other extreme. So over time, that's how that string is moving. Then I'll use purple for the last one. Goes all along like this. So that's how the wave changes over time. I've highlighted the two extremes in a picture down here. So at one moment in time, the wave looks like this. And this is the overall interfered wave made by the incident waves and the reflected wave. So here it is at one moment in time. A half of a period later, it looks like this. Okay, so that's how the wave changes over time, and that's what it looks like. And it looks like a standing wave because we see something that looks like a wave, and this wave nature looks like it's standing still, even though it's made up of interfering waves. So what are some things that we notice? This wave pattern on this particular string is 1.5 wavelengths long. We know it's 1.5 wavelengths long because one wavelength looks like this. So that's what one wavelength looks like, or like this. So there's one wavelength. So that tells us that this entire string is 1.5 wavelengths. We'll be using this idea from time to time, counting wavelengths on the string to figure out some information about the waves. What else do we notice? There are some places on the string where the string doesn't move at all. So those places, I'll get those with a highlighter. So right here, the string doesn't move at all. Right here, the string doesn't move at all. Right here, it doesn't move at all. And here, it doesn't move at all. Those places are called nodes. So if we have a place where the string doesn't move, so right here, right here, right here, those are all called nodes. Label those with an N for nodes. On the next slide, I've got typed up notes that go with this. And then there are places where the string moves the most. So right here, it moves a lot. It oscillates between up and down. Right here, it moves a lot. So there it moves the most, and here it moves the most. Those places where it moves the most, those are called antinodes. So there are two definitions we'll be talking about. What do we notice about the separation of those guys? Well, we see that any two nodes are separated by a half of a wavelength. So there's one bump of a wave between two nodes. And two antinodes are also separated by a half of a wavelength. So two antinodes from here to here is also a half wavelength. So our places with no motion at all, those are nodes. Our places with maximum motion are called antinodes. The places where you have your antinodes, that's where there's maximum constructive interference. The place where you have your nodes, those are places where there's always destructive interference. Your sets of antinodes are always separated by a half of a wavelength, and your sets of nodes are always separated by a half of a wavelength. Something you might like to figure out, it's an easy problem to figure out, how far apart are nodes and antinodes? I'll leave that one to you to work on. So here's just a nicely typed up slide with all of those nodes written on in a readable format. Our nodes are places that don't move at all. There are no motion, goes with the nodes. Nodes are always separated by a half wavelength. Antinodes are places where we have maximum displacement from the equilibrium. Those are places that move the most. Antinodes are separated by a half of a wavelength as well. And then they're labeled in the picture and we show where our half wavelengths go. This is a pretty cool video that either maybe you saw it in high school physics, you might have saw it when you went through chapter 15 in Physics 1050, but we'll look at it again. And it's the Tacoma Narrows Bridge collapse.
Tacoma Bridge, Washington, opened only a few months ago, was built at a cost of over $6 million. But misfortune overtakes the great structure. These are some of the most amazing pictures ever recorded by a newsreel. The actual collapse of the world's third largest suspension bridge. Only a 35-mile-an-hour wind is blowing, but this apparently sets up a rhythmic swinging of the bridge, which increases with each swing. Finally, the swinging road and the suspension cables give way and plunge into the water below. Fortunately, the only casualties were a car stalled on the bridge and a dog.
Okay, so that's a great example of resonance, something that was discussed a lot in chapter 15, but it also applies to what we're doing in this chapter, and I'll just go on to the next slide to show you in particular how this applies to a standing wave. When the bridge was oscillating up and down, and this is just one snapshot taken from the video, if I trace a line along that bridge, so here it is at one time, then a short amount of time later, it was like this. There was actually a standing wave set up on the Tacoma Narrows Bridge. So that's kind of interesting, and it's good that nobody got hurt, even though it was sad that the dog did. But these standing waves are things we can observe in all sorts of places. So now we'll just do one easy example before we move on to some more complicated things. Here's a case where you should pause, see what you think the answer is, and then come back and check. So we're showing a standing wave, like the waves we've discussed already. This wave is drawn showing the two extremes of the wave. So here's the wave at one moment in time. A quarter of a period later, the wave goes down through the equilibrium. And then a half of a period after the start, it's at the other extreme. So this is how we would draw what a standing wave looks like. We show the two extremes, and sometimes we show the equilibrium position. We want to find the wavelength. So what we see is that we have positions marked along our line. Let's think about what does one full wavelength look like. So if we were to draw one full wavelength, we would go from equilibrium up, back to equilibrium, down, back to equilibrium. And then just to complete our picture, we would draw the other extreme of the wave as well. So this is what one wavelength would look like. We compare that to what we see on the picture. So let's draw a line that kind of goes up from here to here, from here to here. So we see one wavelength goes from 0.25 meters to 1.25 meters. So lambda is 1.00 meters. We can read that right off the graph there. So if you said 1 meter, you were absolutely correct.